Hello. So to start this video, going to give you a little bit of background. We are going to be solving our simple system of first order differential equations, which I showed you in class how to set up. We're going to be solving them using Python, as we've talked about so far. Now this is a numerical method for solutions. It's not going to give you a formula. It is going to give you a data set that you can actually plug in and see how it looks. And that's what I want you to understand. We're not getting a function. We're getting data. And this data is going to be a solution to the overall problem. So to start out with, I went ahead and I searched up solving differential equations, ODEs using Python, and specifically I wanted to use the ODEINT function. So I went ahead and Googled that, and I came to AP Monitor, which I think has a really good description of how to do it. So this is ultimately the ODEINT. It requires your model, requires your initial conditions, and it requires your time values. So everything has to be a function of t. So here you're going to want a set of time values. Here, since we have a system of equations, our model is going to be more than one, and similarly our initial conditions are going to be more than one. It's going to have to be listed into a matrix where the first value corresponds to the first model, and the second value corresponds to the second model, etc., etc. So if you scroll down here, this is the basic foundation of what the code looks like. It's pretty straightforward. Here, they set up a function to define the model in terms of t. So here, you have to define t as being some function somewhere. Here they use linspace as a function, a numpy function, to establish that it goes between 0 and 20 seconds, and it creates an array between those two values. And then it goes in here and it says, okay, between 0 and 20, figure out the values of y. So then it gives the dy dt values for all of that. Now you don't know what y is because that ends up being solved by ODEINT. So yeah, that is the function. Now this only shows how to do one equation. And here's the output result. It actually plots it nicely between 0 and 20 because that's the only times when it calculated the solution. But we can have this do multiple models. We can also have it do multiple plots here. So this example shows having 3 different initial values or 3 different target values here for this. It says, okay, so here's the target values, here how k influences when they change k, which k is up here in the model value. That's how they change it for each one of them. And then we can see the 3 plots. Now there's also a few other examples. The one that I am most interested in is this one here that has multiple solutions and the way that they plot them. So here, this was the solution that I ended up going with because it shows you when they did their model, here they have 2 variables. You could mix this with what's shown up here and have 3 variables and vary that 3rd variable so that the different k values are, well, different, so to speak. Alright, sets k equal to 0.1, does it in terms of k is equal to 0.2, does it in terms of k is equal to 0.5, does it in terms of 0.5. So just shows some different ways of changing it. You could go down here and use that too, but I'm just going to basically take this code as is, and because I want to see one solution. So I took this, copied it over, plugged it in, and then when I hit run, you will notice that I get the exact same result that the website did, which that's always a good sign. I did figure out what I was doing wrong with SciPy and NumPy, my previous videos that I put out that hopefully you never watched. But this is correctly working now, and we use NumPy here to plot the solution. So according to this solution, there's two solutions plotted on top of each other, and then they decided to vary the colors and the line type for each of them so that you can kind of see the difference between the two. Now, when I take this function now, and I'm going to go ahead and say, okay, I copied this code directly from here. I'm going to leave that pseudocode in here, so in case I would like to get a little bit more examples, I can. But I'm going to go in here and I'm going to create a brand new program from that after having verified that that one works. Now I'm going to take this and say, okay, let's change the model. So if we go in and we have, let me pop up a text editor real quick. So let's say, I'll just put in my pseudocode. This solves the regular system of ODEs defined by, here, the way that I gave it to you in class was v dot, which is the derivative of v, is equal to, this was f, which is our forcing function, minus alpha, or 2 alpha, times v minus omega n squared times x. Okay, so that's the basic function that we have. The second one that we have is that x dot is equal to v. Those are the two functions for right now. You can write out all of your functions that we have. We'll go ahead and give some and the initial conditions will be v is equal to, I don't know, 2. At t equals 0. And x is equal to, I don't know, 10 at t equals 0. Okay, so that's just some basic parameters of what I'm about to code into this. Now, I've already written out all of this, so I can go ahead and copy this, and here it puts it as these different pieces. I called it dot. This is dx dt, dy dt, dz dt. Nice, that's great. I will go ahead and take this function, copy, and this will be my, it could be any one of these. I'll go ahead and set it to the second function. Paste. So this will be my dv dt. And here my dv dt is going to be my second function. I'll set my dx dt is just going to be equal to v. And this is going to output a z. It's going to require a z and a t, where here the z, I don't believe actually shows up. I go back into here. Yeah, I have a negative z1. So here, z is just some kind of input. Which is great. I guess I don't really need that nearly as much, I don't think. I don't know. Well, I set it to z here, so never mind. That's going to be the return for model, is it gives the derivative dz dt. All right. Yeah, and everything else, I guess, was given as a variable. So that's curious. I will just leave that as is then, because I'm not really sure. Oh, no. We'll try deleting it out. So here, I'm going to have to establish what alpha is, which I will do inside of this function. Alpha is equal to, we'll say it's 5.6. We'll say omega is equal to 1.1. And when I go in here, oh yeah, duh. Your z, this is z1 is the first indicator, which means that you're looking at what I think is your x value here. So here it returns x, y. So here this would be a way of indicating that's x. So that's an x plus 3. Or that's a y plus 3. Oh yeah, no, sorry. Since this is a z1, it's the second entry in that system. So here we do need a z, comma t. And then what we have here is, instead of putting in v, because v is our second entry, this will be z, comma 1. Okay. Here again, v is the z bracket 1, and our x is going to be equal to z bracket 0. Because again, x is the first one, v is the second one. So x being the first one becomes a z bracket 0, and v being the second one becomes a z bracket 1. So you'll have to make sure that that's consistent between how you write it, but we can go ahead and leave it like this. Our initial conditions are, as we put it out here, x first, v second. We could flip that around because that would kind of make more sense, but you know what, I'm going with it. So x first, v second. If I scroll up here, x is equal to 10 at t equals 0, v is equal to 2. So I'll replace this 10 with a 10, and I'll replace this one with a 2. Now we're going to go ahead and go from 0 to 5 seconds. Sounds good to me. Everything else is there. We'll just go ahead and try hitting run. And I will save this one as ODE solver. Okay, instead of hold on Ivana, I'm saving dang it, friggin' dang shoot. I don't even remember what that program was. Oh, I forgot to define my f value. So here I'll have to give my f inside of this function. We'll say f is equal to sine of t. Sure, why not? Oh. Yeah, okay. Sine is not an innate function in Python. NumPy sine function. I'm pretty sure it's through NumPy. NumPy.sine. Show me how to use it. It's NumPy.sine, parentheses, x. Yeah, so that's all it is. It's just NumPy.sine. So, NumPy.sine. Is that how I brought in NumPy? Yeah, it's imported as np. So for here, np.sine, and now I've run it. Oh, bitwise XOR not supported. Nice. Okay, so it didn't like my ODE int model. T first. Interesting. I got it set up right. Goes back to this model here. I believe sine of t, that should produce yeah, if I go back into here, they have each of these equal to some kind of array. So here I got my t in here. I have a t in here. Shouldn't be causing problems with my model. Let's try 0, 0 and see if that just fixes it. If it does, I unfortunately won't know how to fix this. Yeah, okay, that fixed it. Not. Okay, so we go between 0 and 5. This might have no solution. That'd be terrible. It should have a solution though. It's an exponential function. Should be an overdamped system as well. We'll go ahead and just set this one to 5. Try that. Yeah, nope, still doesn't like it. Alright, in another video I wasted everything.